Welcome back, everyone. Today we're looking at active EQs and active filters and how those apply in guitar pedals. The first one that we're going to look at is the tube screamer tone control, but then we're also going to look at some other higher order active filters and where those tend to get applied. But to start with, we're going to look at our tube screamer tone control that we've got here, and this is an active tone section, meaning that it can boost the gain above what the input signal is. Remember, with a passive EQ or a passive tone control, all we can do is take away signal that we don't want. But with an active one, we can actually boost signal that we want while simultaneously getting rid of signal that we don't want. And another benefit of this is that we can, if we have an active tone section like this, it will actually buffer the tone section so that we don't have tone suck, and it will give us a low output impedance so we can drive parts of the circuit downstream without loading them down a lot. So here we have our tube screamer tone control, and if we look at it, it's really just a single op amp gain stage. But there are a couple of things about it that we want to look at and take note of so that we can understand a little bit better exactly what's going on with the tone control here. The first thing is that we have R1 and C1 creating a low pass filter here. Okay? And so before we even go into our op amp stage, we are rolling off some of the high frequency content here. And that obviously is just determined by the values of R1 and C1. Another thing that we have on this stage that it's important to note is we have our bias resistor. It's tying our reference voltage onto the non-inverting terminal of our op amp stage so that we are biasing our op amp stage to the middle of our supply voltage. That's just so that we can swing the signal positive and negative without clipping. And then as we continue along, we see that we have a feedback resistor R3. This is in the feedback loop. Okay. And since this is a non-inverting gain stage, the gain of this stage is determined by the ratio of R3 to the impedance it sees to ground. Okay? And so we have our tone pot right here. And the tone pot is what's going to govern how this tone control is behaving. Okay? So to kind of understand a little bit of exactly what's going on here, we're going to take a look at what the tone control does at the two extremes to help us kind of understand why this setup works the way that it does. Okay, so if we first look at the tone control so that it's all the way to the bass side, then what happens is we have a large resistance here, but this connection goes straight to C2 and R4. Which means that we can rearrange everything so that it looks like this. And so what happens is we end up having our low pass, it goes like this, or our low pass goes like this, but then it's almost like we've got another low pass that comes through here. So we're rolling off quite a bit of the high frequencies. Okay, we're getting rid of a lot of the high frequencies. And then when we have a resistor in the feedback loop of a non-inverting gain stage and there's no connection to ground, then that means that this is just going to be unity gain. Okay, so really what this is doing is it is taking kind of a not quite cascaded, but with this leg and this leg in parallel, we are taking a more extreme low pass filter, meaning more extreme, meaning we have pulled that frequency far further down so that we are now getting rid of a lot more high frequency content, and then we're buffering it. Okay, so this is really just a a buffered RC low pass filter that we've got going on when it's all the way to the bass side. So it's only letting through the really low frequencies, rolling off lots of high frequencies. If instead we look at what happens when we have the tone control all the way to the treble side, or we turn the tone control all the way up, then what happens is it ends up looking like this. So we still have a low pass filter here. This is going to roll off some of the really high frequency content, and that's good because with overdrives and distortions there's lots of upper end harmonics that we may want to get rid of. But now we have our resistor in the feedback loop, and we now have a path that goes to ground. And what ends up happening is that our R11 and R12 here, that will help set the static gain to of the stage. But if we kind of ignore R12 a little bit, we go through R11, we have a node here, and then we go through a capacitor to ground. This is another high pass filter. But because this high pass filter is in the negative feedback loop, or low pass filter, sorry, because this low pass filter is in the negative feedback loop, it ends up acting like a high pass filter. Okay? So because we are running a low pass signal in the negative feedback, the op amp is going to try and compensate, which ends up getting rid of our bass frequencies because it sees an excess of bass here compared to here, so it ends up attenuating the bass signal on our output because of how op amps work. So what this ends up doing then is we have a low pass filter here, we have a high pass filter formed here, so this ends up acting like a band pass filter. So this high pass filter is not attenuating as many highs as in the bass position, which means there's going to be more treble and there's going to be less bass. So it's actually changing the balance of the frequencies on our output so that there is less bass, more highs, and therefore it's a brighter sound because we've turned the tone control all the way up. So we can see that all we're really doing is we're using a low pass on the input and a low pass in the negative feedback loop. And that's creating essentially a band pass on the output. Okay? So that's how this tone control works. It's a very clever way of using an op amp to both create a filter that's not going to load down, but also that's going to accentuate the frequencies the way that you want it. So that's a way that you can use RC filters with active components like op amps. You could do a similar thing with transistors, but transistors are a little bit different in how feedback works and everything. But the principle is the same in that we're using these passive components to change the content, the frequency content of our signal, and then using the active element to buffer those, amplify those, and in some cases using negative feedback, actually canceling out some of those. Now, there are other kinds of active filters that are not just buffered RC filters. Rather, there are a couple of different topologies that are really common in the electronics world. They may not be quite as common in the guitar world as they are in some other areas, but they are still common topologies that it's good to be able to recognize. The first one is the Sallen-Key topology. Now, I've got a low-pass filter here. This is a Sallen-Key low-pass filter. The great thing about this is it's got unity gain here, and it's got we have 4 passive elements, and they are arranged in such a way that this creates a second order low pass filter. Now, what I mean by second order means that it's going to roll off twice as fast as a regular RC filter. So, for example, if we come back up here to our tube screamer control, R1C1 create a first order filter that rolls off at 6 dB per octave. But our Sallen-Key filter is going to roll off at 12 dB per octave, so it's going to be even steeper. This allows you to be able to more tightly control your desired bandwidth of your signal. And in fact, in the pro audio world, doing fourth order filters, which roll off at 24 dB per octave, is really common in high-end systems. So, you can cascade these and build them up to be even more order. But, if we have 4 passive components and our op amp here, what would be the advantage then of setting it up this way versus setting it up as just 2 cascaded RC low pass filters? Well, a Sallen-Key filter is a really awesome topology because the equations to determine everything are really nice and clean, and you can really tightly control the other filter parameters of things like the overshoot, the transient response, things that make the filters different. Because with a single pole filter, a single order filter, it is a very basic, well-defined thing. But once you get into higher order filters, you can start specifying things like overshoot of a filter, which is how far beyond your desired response it ends up going in time. It determines how much the filter rings. There are a lot of really technical, in-depth parameters that you can control more tightly with the Sallen-Key topology than with 2 cascaded RC filters. And in fact, how you choose the different ratios of these components will give you different types of filters. You may have heard of Butterworth filters before, but there are all kinds of filters that have different characteristics to them, and they all are beneficial in their own way. So you can have, aside from Butterworth filters, there are Bessel filters and Chebyshev filters and elliptical filters, and just a whole bunch of different kinds of filters that all have special characteristics, which in the guitar world, we don't tend to be that hung up on it, particularly given the relatively narrow band of frequencies that we deal with. But the Sallen-Key filter is one that does get used occasionally in guitar effects and gets used all over in pro audio. And so it's just good to understand the topology and say, oh, that is a Sallen-Key filter. There are calculators online where you can go and plug your values in and it'll show you what the different characteristics are. Now, another kind of active filter that we see more in the guitar world is actually what's called a multiple feedback filter. And so this here is a second order low pass filter. And this filter topology actually gets used in virtually every PT2399 based circuit. If you notice, if we were to replace 1 and 2 on this op amp with pin 16 and pin 15 of the PT2399, we would be able to see, oh yeah, that's exactly the arrangement that gets used on the input to almost every PT2399 circuit. And the reason for that is because this is an inverting filter stage. Our Sallen-Key is non-inverting, which is really great for certain things. But if we have an inverting op amp stage like this, then what that means is that not only will this give us our 12 dB per octave roll off, so that we're not taking in any really high frequency signal, but it also can act as a summing amplifier. If I wanted to, I could take another resistor here and add it in to this node right here. And I could add a new signal into my path. In fact, this is exactly what is done for the feedback path in a PT2399. And if we wanted to, we can add more and more signals to this node, and this multiple feedback filter will not only filter the signal, but it will also act as a summing amplifier. And so this is why we see it in PT2399 based delays a lot. Now, the disadvantage of this is that it's not really simple to just look at it and know roughly what frequency things are working with. And so there are calculators for this as well. In fact, I'll put a link in the description of lots of a website that has calculators for lots of different filter topologies so that you can go and play around with those. But this multiple feedback filter is really, really handy, particularly in the application of a PT2399 based delay. Now, we have just scratched the surface when it comes to active filters here. These are just some of the most basic ones and most basic examples, or most common examples out there. There are tons more that you can find, but hopefully this gave you an introduction into why we're doing these things and kind of what they look like, so that as you go through schematics, you can look at a certain setup and recognize it for what it is. And we will continue building on this by looking at other kinds of active EQ in the future. Particularly, we'll be looking at graphic EQs and parametric EQs in the future. But until then, take care.